Hello, everyone. What I want to do is go over problems 3 and 4. Most people got 3 and 4 basically right, though I did get some fairly convoluted answers, and I think people were overthinking 3 and 4 quite a bit, particularly problem 3. And I want to go over 3 and 4 because, if you're going to use dyadic intervals, or more realistically, dyadic cubes, and a dyadic cube is just, you take the n-fold product of all dyadic intervals of length 2 to the minus k, and you get dyadic cubes of side length 2 to the minus k, where n is the dimension we're working with. But anyway, yeah, so you don't want to necessarily explicitly write out what these dyadic cubes are in higher dimensions if you ever use them, because you can imagine things are a pain in the ass in the real line, one dimension. For higher dimensions, it's way more convoluted and complicated. So what you do in research when you use dyadic cubes and dyadic intervals, you just really try to only do arguments involving parents, children, and that's basically it, and such notation. Okay, so let's do problem 3, and I'll do that fairly quickly. Okay, so let's say, without loss of generality, we have two dyadic intervals, j and I, and let's say length of j is bigger or equal to the length of I. Okay. Right. So let's get an easy case out of the way. If they're equal, then that means I and j are in Dm for some integer m. And that implies, obviously, I equals j, or they're empty, because dyadic intervals of length 1 over 2 to the m partition the real line. So really not much to do in this case. So let's assume now that the length of j is bigger than the length of I. Okay. And let's say k is, let's say, just like with the hint, it's the base 2 logarithm of the length of j over the length of I. Okay. So in other words, all I'm saying is the length of j is the same thing as, or length of j equals 2 to the k length of I. All right, so this is definitely an integer, a positive integer, because the length of j is bigger than the length of I. And this is an integer because these lengths are of the form 1 over 2 to an integer. So anyway. Okay, so let's assume I intersect j is not empty. Okay. Okay. Right. So let's assume j is not the kth parent of I, or the kth generation parent of I. So there's nothing really needed to prove here. So I proved in lecture that there is a first generation parent. So just to remind you here, we keep going and going. So I tilde of 2 is just the parent of I tilde, et cetera, et cetera. And you keep doing this. And so this here, I'll do it in red. So this is the length of I. It's kind of trivial. 2 times the length of I, et cetera, et cetera. So here is I tilde of k. And so this has length to the KL of I. And lo and behold, that's the length of j. Okay? So all I'm doing now is assuming, and this is kind of what I meant by really do this whole problem in one bang. Yeah, anyway, of course, the length of I tilde 2 is 4 times the length of I, but anyway. And this is I tilde of k. Okay, so if this is the case, then, right, I intersect j is certainly a subset of let's see. Whoops. Yeah, that's fine. I tilde k intersect j. That's pretty trivial. I tilde of k is whoops. Sorry, these are going the wrong way. Let's sorry about that. Okay, yeah. So this is larger. So this is possibly a larger set. Okay. So if this is not empty, then this is not empty. Okay. On the other hand, j and I tilde of k are both in really specify not really let's say dm. Well, m is going to be well, whatever. It doesn't even matter what m is. It's so the point is that these are in some common dm because they both have the same length, 2 to the k length of I. So whatever m is doesn't matter. Right. So we have 2 dyadic intervals in dm that have non-empty intersection, but dm partitions the real line. So that implies that j has to be the kth parent of I, kth generation parent of I. That implies, or in particular, that implies from right here, I is a subset of j. Right. So, and yeah, you know, if the length of, well, the length of I is bigger than the length of j, basically, same thing to swap the roles. So, right. And the second part we've basically already proved already. Okay. Okay. So I'll just emphasize. I'll just reprove it, but we really already proved it. Or maybe, yeah, let's assume j is strictly larger you know, let's assume j is strictly larger than I. Well, yeah, so really, sorry about that. So if this is true, then I intersect j is not empty. And obviously the length of j it's not equal. It's bigger or equal to length of I. And we exactly proved that in this case, j has to be the kth generation parent of I for some k, could be 0, which we define this as I. If the length of j equals the length of I, then these are equal. If it's positive, we prove that this is true right here for k an integer. So in general, for a non-negative integer. Okay, that's really all there is to the proof. And again, the point I'm trying to emphasize is avoiding writing out explicitly what these dyadic intervals are. We really only have to do that once, and we did that proving the existence of a dyadic parent. Once you prove the existence of a dyadic parent, you really don't have to explicitly write out these dyadic intervals. You just have to use basic properties of dyadic intervals. Okay. Okay, and similar for problem 4. So let me go back to problem 4. So what's problem 4? Remember, problem 4 is if f is a real function, and we define the i's and j's in this way, then fk goes to f uniformly. And in particular, this is a very canonical and simple way to uniformly approximate a function by simple functions, or maybe not necessarily. Well, I mean, technically, this is a infinite sum of infinite sum of characteristic functions, but almost simple functions in a monotone way. Okay, so right. Certainly, if f is bounded, this will be a simple function because there's only going to be a finite number of non-empty j's. But anyway, all right. So right. So most people got the uniform convergence part, but not everyone. So I just want to go over that. It's going to be very quick. Okay. So right, fixed k. And that, so for fixed k, there is some L, because obviously partitions the real line, these intervals. Okay, so sorry, f of x. So x is in the inverse image. Nothing to this, of course. Everyone got this part right. Okay, and because of that, and because these are clearly disjoint, the JLKs, just because these dyadic intervals are disjoint for each fixed k. So that implies, because x is in JLK, and if x is in JLK, that implies fk of x, by definition, literally by definition, is L minus 1 over 2 to the k. Okay. So that implies f of x minus fk of x, well, this is going to be minus L minus 1 over 2 to the k. Well, f of x is in this interval, so the most this could be is when f of x is L over 2 to the k, in which case this is L over 2 to the k minus L minus 1 over 2 to the k. So it's at most 1 over 2 to the k. You can't really do any estimating with L because you have absolutely no idea what L is. Even if k is small, you could have f of x really large, in which case L is large. There's no relation between L and k. There just is none. Okay, so that shows uniform convergence. There's no x here. So, okay, so the second part, right. So for the second part, now let's say f of x is in this dyadic interval IL. Okay. And let's say I don't know what to call it, but IL prime k minus 1. Let's say this is the parent. Okay, so this means that, well, obviously, because it's a parent, yeah, ILK is a strict subset of IL prime k minus 1. Okay. Okay, so if ILK is ALBL, really care what these are at this point. And if this is AL prime, for lack of anything better to call it, BL prime, okay, then, so really the point here is just a little notation saving fact here is that if f of x is in this interval, then fk of x is just the left endpoint of this interval. Okay, that's all this means here. Like we've seen before, this means f of x, or rather, if x is in JLK, then f of x is in this interval, and that means fk of x is the left endpoint of this interval, which is L minus 1 over 2 to the k. So with this in mind, now we just can easily figure out what's what. So fk of x minus 1, that's going to be the left endpoint here. That's AL prime. Okay, well, so we have that ALK is a subset of AK minus 1L prime. So in particular, AL, so let's write that here. AL is in this set here, so AL is bigger or equal to, or rather, AL prime is less than or equal to AL, because AL is bigger or equal to AL prime. Okay, and this is what FK of X is going to be. Right? So maybe to be clear, X definition, sorry, f of x is in here, so f of x is in this one, so by definition, f of x is in J L prime k minus 1, and hence fk of x is this left endpoint. And this was just done for arbitrary x, so that's it. There's nothing more to it. So you really, yeah, you don't really at all care about the nature of these endpoints. We're really just literally using nothing more than the existence of a parent and the fact that for each k, these dyadic intervals um, partition a real line. So yeah. So if we had more time, we would do a lot more with dyadic intervals. In particular, you can come up with a very canonical orthonormal basis of L2 for, with respect to dyadic intervals. It's called the Haar basis. You might have heard that. It's basically like the Haar wavelet, same thing. But anyway, all right. Well, have a good break, and if you want to submit homework 7 anytime, I'll be happy to look it over. If not, no big deal. So, all right, take care. Bye-bye.